Okay, hi. So in this video, I am trying to keep it as short as possible. So I decided to write out the information rather than writing it in real time to make the video very short. So what we are briefly going to describe is the small signal analysis, and that will also bring out the whole idea of transconductance very well. So a transistor, by definition, can be a voltage controlled current, yes, source, sorry. So I didn't bring out, so a voltage controlled current source. So that means that you have this current IC being drawn from VC here, the power supply here, but then it's being controlled by another voltage, not necessarily, even though VC is the one supplying it. So if I change the value of VC, if only VC is capable of producing the current, it shouldn't change. That would be an ideal current source. But of course, from early voltage, we know we might not get an ideal current source. So that's the whole idea why a transistor is called a voltage controlled current source. We know there are other conditions. It should operate in the forward active region. Okay, so it would be ideal if we ignored early effect. So the whole idea of transconductance comes in, as previous videos have already made this characteristic curve here. Let me change to the highlighter. So this characteristic curve here clearer. So what we see here is, assuming the transistor is operating at a particular base emitter voltage, VBE1 as it's called, just around it, the curve itself is a nonlinear curve, it's an exponential curve. But for small regions around the bias point, if I bring a signal, that will be changing or varying slightly around the bias point, as you are seeing here. Now, where small here in this case will mean voltage changes which are far lesser than 26 millivolts, which is the terminal voltage. Okay, so in that case, then we can linearize the curve. So I can draw a straight curve, I can superimpose a straight curve on the exponential curve, but as I draw the line longer, then I'll lose the required characteristics. So that's clearer here. If you look at this curve, I could linearize it within a very short window where this change is less than 26 millivolt. But if the change became bigger, then it wouldn't make sense for me to linearize the characteristic between the voltage and the current. So it will no longer have that Ohm's law definition behavior. Okay, so that sends us to the definition of transconductance. And there are two definitions, one that works always and one that only works for small signals. So back to the highlighter. So at or around a bias point, so a bias point will be around a fixed VBE. If I introduce a signal and that signal brings some small changes, then if I differentiate the current, small changes in current with respect to small changes in the VBE will give me the transconductance. And I can rewrite this in this formula, that the change in current is equal to the transconductance, which by definition we'll see very soon why it's like this, is equal to this. So there will be a linear relation between the current and the voltage. As you can see here, only occurs in small changes. So changing the color again. So around here, only small changes, they have that linear relationship between the voltage and the current. So it's very important for you to be able to visualize this part very well so that I get a better understanding. But what is always true regardless is that IC, of course we are ignoring early voltage, is equal to the reverse saturation current times this exponential VBE VT. And if you differentiate this with respect to voltage, then you're going to get all this divided by VT. And since this term here is the same as IC, then you can also say that, okay, always say that, okay, then a change in current with respect to voltage, which is the definition of transconductance, is given by this. So for the transistor to operate as a current source, a voltage dependent current source, the definition of the transconductance is how much voltage is able to change how much current, and that is transconductance. That's the definition. So transconductance is just a ratio of changing current over changing voltage. So just make sure you don't get confused with the small changes formula and the general formula that always work. So in this case, the transconductance here can be calculated using the bias set point. So if you go back to this curve, if the bias set point is at this point, then the transconductance here will be larger. So changes in voltage around this point will be bigger compared corresponding changes in current with the same change in voltage will be bigger around this bias point compared to the corresponding change in current around this bias point. So that's why, so we can clearly see that the transconductance with a higher VBE is greater than the transconductance with a lower VBE, and that makes sense if the transconductance are also functions of IC. So the VBE here corresponds to a bigger value of IC, so IC2, and the VBE1 corresponds to a smaller value of IC, which is IC1. And you know the transconductance GM1 will be equal to IC1 over BT. Okay, so I move to the next page, and small signal model. So for the small signal model, if we are looking at only the signal changes, so we can look at a fixed bias point and small changes. So if I'm looking at this, I have the transistor biased to get a particular transconductance or a particular IC which is fixed before the transistor can operate properly. Depending on how much gain I want, I need to set the bias voltage to fix that. Then the signal comes in from a microphone, which is easier to understand, giving changes in, let's say, plus or minus 10 millivolts. Easier to use these values as an example. Okay, so we can model that in what we call the small signal model. And in this small signal model, what we have is we have the base of the transistor, the base here, and it connects to the between the base and the emitter. There is this junction here. So we can replace the junction with usually it's replaced with, let me change the color, it's replaced with a resistor. If you recall, for diodes too, there is that small changes resistance that can represent a diode. So we call this R pi, which is very important. And in this case, because there's a ground, so the emitter is grounded, and we can just join them this way. So what happens is that the voltage applied here, if I apply some form of voltage here, V1, whatever, VB, VBE, now that voltage will also be across this resistor here. And the voltage across this resistor here, let's just call it V pi, would be the one affecting, so let me just make this one also V pi consistent. We know that in this particular instance, VBE and V pi are the same. So in this case, any change in VBE, the voltage I'm applying here, affects the collector current. And because we're only dealing in small changes here, that's why there's a linear relation here. So it's good, take your time. If you didn't get this very well, go back, begin the video, make sure you understand these concepts, because it's very crucial for you to understand small signal analysis. Okay, so what we have is there is a fixed point which is caused by the fixed bias, so we call that the bias point, and this current is defined by this. And when I bring in a microphone to in series with the bias, the microphone, so assuming the microphone alone would have been, the signal of the microphone would be this way on oscillating around 0. Now if I add that to the VBE, it's going to raise, that's what we call a DC offset. So it's going to raise the microphone signals with a DC offset. Instead of oscillating around 0, we'll now be oscillating around the VBE fixed. And the VBE fixed alone will cause IC, which can be calculated by this. So this IC is the fixed IC, and it's the same IC that is used to calculate the transconductance. So now the changes in the signal in the input side from the microphone will also cause some changes in the output, and that is what we use to calculate for the gain. So the changes in the input signal, the 10 millivolt plus, and the output, which will be the microphone signal times the transconductance, gives me a current, multiplied by the collector resistance will give me the output voltage. So if the output voltage, I think it's written, okay, so the input voltage from the microphone is plus or minus 10 millivolts sinusoid, and the output voltage is this small signal current times the resistor, because we need a resistor to change current. This term alone is current. To change current into a voltage, we need to multiply the current by resistance, and when that is done, we now have the output voltage giving us this. So if you want to find the voltage gain, okay, also there is a phase shift of 180, because in natural sense, as explained earlier, if you have the collector resistance this way and current moving through that, the output is taken after the drop. So the higher the current, the higher the drop, the lower the output. So if the drop is increasing, then the output is reducing. That's why there's a phase shift there. I think that has been explained. You can watch earlier videos to understand that concept better. So once we know the output and the input, we divide the output by the input, which is the plus of 10 millivolts, and the gain of the transistor with the phase shift becomes negative GM RC, which is the gain of the common emitter stage. Why we call it common emitter stage is a story for another video. So finally, we have our gain given as this. Okay, so I hope it was short enough, and I hope you enjoyed it. Take your time, pause when you need to pause. If you have any question, you can leave it in the comment section. Have a nice time. Bye.